So, we all know that pure water boils at 100 degrees Celsius, which is equal to 373.15 Kelvin. As we go down the temperature scale, we reach 37 degrees Celsius, and this is the typical temperature of the human body. As we continue to descend the scale, pure water is at its highest density at 4 degrees Celsius, which is 277.15 Kelvin. So clearly we can go further and further and furthermore down the scale. But will we reach a limit? What will the limit be? And what happens at temperatures near the limit? There is, in fact, a limit. The limit is termed absolute zero, which measures exactly 0 degrees on the Kelvin scale and negative 273.15 degrees on the Celsius scale. This is the coldest theoretical temperature on the thermodynamic scale, and at this point all particles of matter have no thermal motion and are at the lowest states of energy. That's very, very, very cold. Scientists have only been able to achieve temperatures close to absolute zero. The lowest temperature that has been reached on Earth is 0.45 nanokelvin, which was achieved in year 2003 by a team of scientists at the Massachusetts Institute of Technology using a cloud of sodium atoms. Naturally, the coldest known place in the universe is the Boomerang Nebula. It is 5,000 light years away from Earth and has steadily maintained its temperature of 1 Kelvin, making it only 1 degree above absolute zero. You may be wondering whether we can ever reach absolute zero. However, I have to tell you that it is unfortunately impossible to do so. There are many reasons for this, including Heisenberg's uncertainty principle, as well as the third law of thermodynamics. Even so, there are many fascinating things that happen at very low temperatures. Firstly, I must introduce you to the phenomenon of superfluidity. Superfluidity is a state of matter in which the matter behaves like a fluid without any viscosity. Helium gas condenses to a liquid at 4.2 Kelvin, and when liquid helium is cooled down to a mere 2.17 Kelvin, it displays superfluid characteristics. This temperature is called the critical point and is characterized by a jump in specific heat capacity and a discontinuity in its density graph. Superfluid helium looks like any other ordinary liquid, but it flows without friction along any surface and can also flow up the walls of its containers. This is called film flow, and it seems to travel in a way that defies gravity and surface tension. As a result, superfluid helium is used as a quantum solvent to dissolve gas particles, as it provides a zero friction environment. A single atom or molecule being dissolved in it allows the particle to effectively have rotational freedom, which imitates the particle in its gas phase. Another very intriguing phenomenon that occurs at temperatures near absolute zero is superconductivity. Certain metals, such as aluminium, mercury and zinc, when cooled down to such temperatures, have no electrical resistance at all. This means that a current, even without a constant source of power, can flow infinitely in a loop of wire made of a superconductor, provided that the superconductor remains at a low temperature. Due to the fact that there is no loss of energy resulting from electrical resistance, superconductors bring us many practical applications, including creating more efficient electromagnets, maglev trains, particle accelerators, and nuclear magnetic resonance machines, just to name a few. I hope you enjoyed the video and that you took something away with you in this small introduction into this fascinating aspect of physics, and of course recognise the potential it has in future physics.